Look at data flowing through modern enterprise architecture. AI inference models, vector databases, and microservices consume and generate data at blistering speeds. To function, they require real-time, continuous access to decryption keys. But securing those keys relies on methods built for a slower era. Techniques like Shamir's secret sharing require multiple human operators to physically provide key shards just to unlock a system. If a server crashes or a cluster restarts at 2 a.m., the deployment pipeline grinds to a halt. The system sits locked, waiting for human intervention to piece the shards back together. Placing root keys in human hands expands the attack surface. Every time an operator handles a key component, there is a risk of exposure or theft. Security protocols requiring manual intervention cannot survive the scale and velocity of modern workloads. They break down exactly when you need them to perform. We are integrating two entirely distinct environments. The hardware security module provides a dedicated physical root of trust, while HashiCorp Vault operates as a flexible, software-defined control plane. To achieve true enterprise key governance, you need a zero-touch architecture that bridges these two environments. This diagram outlines a 10-step automated lifecycle that integrates hardware generation with active software monitoring. Notice the three distinct zones: the hardware boundary on the left, the control plane in the center, and the application zone on the right. By mapping this precise path, organizations eliminate static credentials from their network while maintaining an unbroken hardware-backed chain of trust. Delegating this trust dynamically means developers secure massive AI workloads without introducing latency or throttling system performance. Effective enterprise security relies on an unbroken, automated governance lifecycle that extends from the initial key generation to active usage monitoring. The lifecycle begins on the far left. Step 1. The HSM generates the master root key. This key is cryptographically bound and must never leave the hardware boundary. To bridge this physical device with software, we use Step 2, the PKCS SHOP 11 standard. Vault is configured with a PKCS SHOP 11 seal block to use this precise channel. This creates a secure cryptographic handshake. Vault sends requests down the line. The HSM executes the operation internally and returns the result, while the root key remains completely stationary. For a DevSecOps engineer, this means pointing Vault's configuration files directly at the HSM's cryptographic library, mapping the slot and token labels exactly. Locking the root key in hardware via PKCS SHOP 11 establishes an immutable anchor of trust. Even if software is compromised, the core cryptographic material remains untouchable. Let's shift focus to the center control plane during a system restart. The Vault node powers on, but starts in a sealed state. Vault knows where its storage backend is located, but lacks the cryptographic master key required to read the data. Without automation, the system is deadlocked, requiring manual intervention. Instead, for Step 4, Vault autonomously sends an encrypted payload down the PKCSS11 channel. In Step 5, the HSM uses the root key to decrypt this data, securely exposing Vault's master key. This decryption occurs strictly within the physical hardware limits, safe from attackers. For Step 6, the HSM returns the decrypted master key into Vault's active memory. The padlock vanishes, and the Vault node finally becomes active. Disaster recovery is no longer a manual chore. Auto-unseal converts it into a secure machine-to-machine protocol. Moving into the application zone, an AI inference pod initiates a request to the unsealed Vault node. For Step 7, Vault evaluates this call against its policy engine. Instead of a permanent password, Vault dynamically issues a short-lived, ephemeral credential. In legacy systems, static keys sit indefinitely. A zero-trust model ensures credentials expire before attackers can weaponize them. For Step 8, the microservice utilizes this timer-bound credential to access and decrypt the target payload before the key expires. In modern architectures, these payloads contain sensitive assets, AI model weights like vector embeddings, and proprietary business data. Coupling hardware-backed trust with ephemeral software access allows applications to retrieve data at high velocity without expanding the long-term attack surface. Decryption is not the final step of the lifecycle. A secure architecture also requires continuous verification. This brings us to Step 9, Comprehensive Observability. Vault records every unseal event, policy check, and ephemeral key fetch. The audit log captures identity, actions, and timestamps. To close the loop, Step 10 integrates a SIEM system. The SIEM actively scans for deviations, instantly flagging anomalous consumption patterns, unusual key requests, or queries from unauthorized subnets. A zero-trust architecture requires this closed loop. Rigorous logging and active monitoring convert passive cryptographic defenses into an active threat hunting engine. Pulling back to the full 10-step architecture, we see continuous, healthy data flowing from the physical hardware on the left all the way to the application and monitoring layers on the right. This structure establishes a high-velocity operational pipeline, where keys move at digital speed while remaining tethered to hardware-backed security. Each component performs a specialized role. The HSM protects the root key at the physical layer, Vault governs zero-trust policy and ephemeral access at the software layer, and the SIEM ensures total accountability. For DevSecOps engineers, this specific configuration is the mandatory blueprint for scaling secure AI and microservice infrastructure. Taking shortcuts compromises the model. Bypassing the hardware root of trust leaves keys exposed to software vulnerabilities, and ignoring the SIEM integration hides potential breaches. By implementing this precise HSM Vault lifecycle, organizations prove that uncompromising cryptographic security and high-velocity automation can function as a single, unified system.